I'd like to welcome our next speakers. So we have two, Levin and Cohen, and they're presenting Guided Walk, a Scalable Recommendation Algorithm for Complex Heterogeneous Social Networks.
Okay, so good afternoon, everyone. My name is Levin from Microsoft. And I'd like to present this work about a model called Guided Walk. It's a recommender system for enterprise social networks. This work was done while I was at the IBM with Hassan, Abassi, and Cohen, which will present our experimental evaluation part. Okay, so let's start with the motivation. And so enterprise social networks, they tend to form complex heterogeneous structures. That basically means that we have many different types of social entities, employees, wikis, blogs, communities, and so on. And there are also complex relationships between these entities. One employee can manage another, there could be colleagues, community can contain blogs, and so on. And so we want a recommender system that takes into account all this complex structure and is also supervised. So let's look at this example over here. Here in this example, first we have our hierarchy between the entity types, between the different entity types. So we have a community containing a blog, which contains an article and a comment. And it so happens that Chris, which manages Bob, liked the comment, which was written by Anna. So now we want to be able to answer the question, will Bob be interested in this blog? Can we say anything intelligent about that? So apparently we can, but first we have to use the correct model. And let's think for a minute about collaborative filtering as a model. So collaborative filtering is widely used in recommendation systems. And the intuition with collaborative filtering, the model, what it tries to do is to predict or approximate unknown ratings, unknown user item ratings based on the known user item ratings. And so it creates the bipartite graph between users and items and performs all its calculations. But here we have a complex structure. We have a complex structure, like I said, between the entities, between the employees, and collaborative filtering does not take that into account. So that is a problem. And so to kind of create a quick mapping of the different type of research that is involved in recommender systems, we could look at it in this way. We have the unsupervised models, and we have the structure of the data, which can be simple, a bipartite graph, or even sometimes just items, and we have maybe content-based recommendations, and we have the complex structure. Then we have a supervised or unsupervised. So where we want to be is in the supervised and complex structure. This is where our model works. Okay, so let's look at the solution. So the main idea is that we can create a graph for each user. And then what we want to do is we want to learn the probabilities, the edge probabilities, the transition probabilities between all the different entities based on what users actually liked. And when I say like here, I mean it in the more general sense, whatever the user was interested in. We'll just use that interchangeably when we say like. And after we do that, we can then compute the top k items based on path probabilities, which are based on these probabilities that we've calculated based on the likes. So let's see how that works with this example. So we have our user. We want to recommend something for the user. We know that the user liked our orange items over here. And these are the candidates. The blue items are the candidates. Which blue candidate should we recommend in this example? So let's look at that a little bit deeper. The first thing that pops here is the fact that the left path does not involve any likes of the user. So it doesn't seem like item C1 is a very good recommendation because there's no indication here from the user likes that there are paths leading to C1 that should be of interest to the user. Whereas C2 and C3 both have paths that lead to likes, and so we have to decide which one of them is better. So the idea is to count the relative number of times each edge is traversed in all the paths leading from the user to its liked items. After we do that, after we calculate these probabilities based on these counts, we can then recommend the vertices based on calculating the expectation from the user with respect to these counts that we've calculated. So let's look at an example. This is a conceptual example of how the algorithm works. So we have here a pair of two counts. The first count counts the number of paths with user likes. The second count is the number of paths to leaves in general. So here we look at the first path. Since it didn't lead to any likes, we just increment our second counter, the counter for leaves. Then we go on, we continue to update the counts. We still don't have any likes, so our first index is still 0. Now we finally reach the like, so we increment the counter, and so on. We continue, and you could see how the counts get updated. In practice, for efficiency reason, it doesn't really work by enumerating all the paths. It works more efficiently than that, but the details are too complex to go into in the slides, so I encourage you to read the paper. So finally, after we have these counts, we could learn our weights for the edges, learn the different weights, and these are the weights that we get. But then there's a problem that we see right away. The problem is that some of our edges have a weight of 0. And if we're going to draw probabilities from these 0 weights, we're going to have a problem since all the paths are going to have 0 weights, 0 probability because of the 0 weights. So how can we correct that? Obviously, we can see that if we follow the path until we reach this 0 edge, there is a big difference between the paths. But this 0 edge, if we just multiply these weights, at the end it's going to be 0. So how do we fix that? We need something to smooth these weights. So what we do is we use Laplace smoothing, which is similar to what's used in naive Bayes classifiers. It's basically a technique to avoid overfitting. We just add a certain epsilon to each weight, and that solves the problem of the 0 weights. Once we do that, we can simply calculate the score for our candidates by summing up all the path probabilities. And so in the example we showed earlier, eventually what we'll see is that item C2 gets recommended first, and indeed C1 is going to be recommended last because it's a path of epsilons, and this path is going to get a very low probability because epsilon is low. So it's also interesting to note that C2 is ranked higher than C3, and the reason for that is that you could see that the edges that are involved in the path leading to it, they have a higher probability of leading to likes, even though this path leads to more likes. But there are also more paths on the right-hand side. So there are more paths with likes, but there are also even more paths. So this calculation shows that despite the fact that there are more likes on the right-hand side, in proportion to the total number of paths, it's not significant enough, and so we prefer this item. So there are a few challenges here, like I said. So enumerating all the possible paths is not feasible. So we have to formulate this as an iterative algorithm. I encourage you again to read the paper for that. And the other thing is the graph itself is too large to be processed by a single node, by a single machine. So what we did is we formulated the problem as a Pregel algorithm. Pregel is basically the MapReduce for graph processing. It's a framework for large-scale graph processing. It lets you specify your algorithm using those primitives from Pregel, and then it gets run in parallel, distributed over many machines. All right, so the experimental evaluation, you'll see.
Hi, I'm Uzi from IBM Research. I'm going to present the evaluation part of the paper. In order to properly evaluate our work, we implemented 4 different algorithms. The first one is the guided walk that was presented by Roy earlier. The second one is the basic collaborative filtering. For that purpose, we used the Spark MLlib implementation. The third one is the personalized random walk, which is the basic random walk that uses uniform distribution given a vertex. And the fourth and last one is the popular neighbors that is not a personalized algorithm, but simply an algorithm that gives weights to more popular vertices. The data set we used is IBM Connections, which is an enterprise social network used by IBM and other companies. At the time of the paper, we had something like several hundred of millions of vertices and edges, but as we noted, we extract a subgraph from this huge graph. We called it the user graph. In order to examine the performance of our algorithm, we devised an offline experiment. The offline experiment used 4 months of user logs and activities in order to learn the edges probabilities. Then we produced recommendation, which included 1,100 IBM users. Then we compared it with future user activity. This data was taken from 2 unseen months of activities, and then we measured regular measurement values, such as map at 50, map at 10, map at 50, and map at 100. The results of the offline experiment is showed in this slide. Guided walk, which is the algorithm we implemented, was 3.6 times better than the second best algorithm. We used another random recommendation mechanism just to make sure that all other algorithms performed well in order to ensure that other algorithms were good enough to measure against. The main drawback of the offline experiment is that the recommendations weren't actually shown to the user. This means that we used only prediction-based evaluation. And the more important question in our mind was what the user potentially would have adopted in case he actually was shown the recommendations. In order to address this challenge or this issue, we facilitated another experiment, the online experiment. In this experiment, we used 2 months of activity of users, of IBM Connections users, in order to learn probabilities of the edges. Then we produced recommendations of 373 highly active IBM Connections users. We conducted a survey in which we gave each user top 3 recommendations from each algorithm, shuffled, and then each user was asked to rate 0 to 3 for each recommendation, where 0 reflects not relevant and 3 very relevant recommendation. The results of the online experiment implies that there is a slight change in the ranking of the other recommendation algorithms. In the paper, we thoroughly explain the concept behind this re-rank. But the good news for us was that we outperformed the second best algorithm by something like 14%. And this measurement was simply take the average rating of the user. To summarize what we did, we wanted to address the problem of giving a recommendation in complex structures. In our case, the enterprise social network. We presented a novel algorithm we called guided walk, which was implemented as a Pregel algorithm. And we outperformed the other baseline algorithms, as we showed in the offline and online evaluation results. Thank you very much.
Thank you. Do we have any questions from the audience?
I was just curious how explore part would work. You could recommend very relevant items, but there might be no surprise in the recommendation with this approach. I want to find something interesting, for example, but it will give the best relevant one, but it will not give interesting results. Explore part.
Well, interest, what we focused on was relevancy, okay? We want to find items that are relevant. Now, interest is a little bit, the question itself is a little bit different. We actually found out about this while we prepared the survey. The term interest also refers to how interesting the items themselves in, say, the social network are. Maybe the items themselves are not that interesting, then the recommender system cannot be at fault that the items are not interesting in the social network in general, right? And we're not trying to find out how interesting the social network is in general. We're trying to answer a different question, how to find the most relevant items within the social network. So when we asked the questions in the survey, we asked specifically about relevance. So we didn't do anything in general about interest. That was kind of beyond the scope of this work. I hope that answers the question.
Do you have any more questions? Okay, can we thank our speakers? And